Hello, I'm Giovanni Grau, and today I'm going to present our TSE Journal first paper titled Testing with Fewer Resources, Adaptive Approach Performance-Aware Test Case Generation. Testing plays an essential role in delivering high-quality software, but it's also a burden in terms of time and cost for developers. To alleviate such a problem, a lot of research has been done in the field of test case generation in the last decades, mainly exploiting evolutionary search and genetic algorithms in particular. These algorithms aim at maximizing various testing criteria, and most of the scientific effort so far has been targeted in maximizing code coverage, for instance, branch coverage. However, code coverage is not the only desirable aspect for test cases. Indeed, the test readability, code quality, execution time, memory usage are all desirable features that we would like to maximize. A large body of research tried to optimize those qualities along with code coverage. However, they fell short in doing so while keeping code coverage high. In this work, we focus on execution time and heap memory consumption as the qualities of tests we want to optimize. We extend aDynaMOSA, state-of-the-art for multi-target algorithms, by proposing adaptive aDynaMOSA. In this work, we face two main challenges. The first is about doing test performance analysis into the main loop of the algorithm, without detrimental effects on the performances. The second, as said, is to optimize a non-coverage criteria while keeping high the final code coverage. Let us see now how can we tackle the first challenge. For our approach, we needed to measure test run time and memory consumption to favor the test with better values. The ideal way to do so is to profile and run a test multiple times and measure the performances. However, this is not feasible in the loop of a genetic algorithm, since this will terribly slow down the performances. Thus, we devised 7 performance proxies that are fast to compute. They can approximate a more rigorous performance measurements of a test. Therefore, we combine them in a so-called performance score after normalization. Now let us look at how we can include this score in the main algorithm to address the second challenge. So starting from an initial population, aDynaMOSA generates offsprings and ranks them into fronts. When picking the best individuals that need to survive to the next generation, the algorithm picks individuals starting from the first front. In each of those fronts, the approach uses a metric called crowing distance that promotes diversity in the test within each front. This metric is very important for evolutionary algorithms since it prevents stagnation in local optima. Thus, this metric favors high code coverage. In our approach, we use both crowing distance and the performance score in an adaptive way. We start with performance score to rank individuals in a front. As soon as we detect stagnation in the fitness function, so in other words, the algorithm is not increasing code coverage anymore, we switch to the usage of crowing distance. And we do this switch in an adaptive way, looking at the situation of the fitness function. When crowing distance is used, more diverse tests are selected. When the performance score is used, tests with lower resource demands are favored. To evaluate aDynaMOSA, we selected 110 Java classes from 27 different projects, coming from different benchmarks. We used aDynaMOSA as a baseline, and we asked ourselves 3 research questions. What happened to the branch coverage? Can we achieve the same mutation score? And can we reduce test run time and in-memory consumption? In a nutshell, we had very similar performance in terms of code coverage. We achieved the same average coverage over the context of the study, and for a large part of the classes, we had no significant difference in terms of achieved coverage. And the results are very similar when we look at the mutation score. We still have a pretty similar average score, and for a large part of the classes, we don't have any significant difference. So in a nutshell, we can achieve the same code coverage and same mutation score as the baseline. To evaluate the last research question, we took the subjects achieving the same code coverage from both the approaches. Then we took the test suite generated, and we ran this time a rigorous performance measured process, the one that was not possible to do into the genetic algorithm loop. So we profiled these suites We ran them for 100 times on a bare metal server machine in a fresh JVM, and we collected in-memory consumption and runtime. So bottom line, we have an average, 72% lower runtime and 70% lower in-memory consumption. So result is that with same coverage, we are able to have lower resource demands. To wrap up, we introduced adaptive aDynaMOSA, that is an adaptive approach that is able to optimize secondary objectives that is orthogonal to code coverage without any negative effect on the code coverage itself. In this paper, we focus the problem of generating tests with low resource demands. In this case, runtime and in-memory consumption. But this is a flexible algorithm that can be used in theory for any kind of secondary objective. And this is also part of our future research. At the end of this slide, you can find the link to the preprint. And thank you for the attention. Hope you enjoyed this talk. Thank you very much.